Time flows around us like an invisible river, carrying us from one moment to the next. We measure it with clocks, mark it with calendars, and feel it in the beating of our hearts. Yet, what if everything we think we know about time is wrong? What if time itself is not the fundamental force we believe it to be, but rather an elaborate illusion created by something far more basic, something that surrounds us constantly, yet remains largely invisible to our everyday experience? Tonight we embark on a journey through the cosmos to explore one of the most profound questions in physics and philosophy. Could time, as we experience it, be nothing more than an illusion shaped by the speed of light? This idea challenges our most basic assumptions about reality and invites us to reconsider the very nature of existence itself. Imagine standing in a field at night, looking up at the stars. The light from those distant suns has traveled for years, decades, even centuries to reach your eyes. In a very real sense, you are not seeing the stars as they are now, but as they were in the past. The light carries with it a kind of temporal signature, a record of when it began its journey across the void. This simple observation hints at something deeper, something that connects the speed of light to our perception of when events occur. As we gaze into the night sky, we are witnesses to a cosmic light show that spans eons. Each photon that enters our eyes is a messenger from the past, carrying information across the vast distances of space. But these messengers do not travel instantaneously. They move at a specific speed, exactly 299,792,458 meters per second. This speed is not arbitrary. It appears to be woven into the very fabric of reality itself. The speed of light serves as more than just a cosmic speed limit. It may be the key to understanding why we experience time the way we do. When we look at distant galaxies, we see them not as they are, but as they were millions of years ago. When we observe the sun, we see it as it appeared 8 minutes in the past. Even when we look at our own reflection in a mirror, we see ourselves as we were a tiny fraction of a second ago. Light creates a universal delay, a gap between when events happen and when we can observe them. This delay suggests something remarkable. Our entire experience of the present moment may be constructed from information that is perpetually arriving from the past. We live in a world where the now we experience is actually a carefully orchestrated collection of then moments, all arriving at slightly different times, but woven together by our brains into what feels like a coherent present. But the relationship between light and time goes even deeper than this observational delay. According to Einstein's theories, space and time are not separate entities, but are joined together in a single fabric called space-time. Light moves through this fabric, and as it does, it reveals something extraordinary. Time is not absolute. It does not flow at the same rate everywhere in the universe. Instead, the passage of time depends on how fast you are moving and how strong the gravitational field is around you. Near massive objects like stars or black holes, time slows down. For objects moving at speeds close to the speed of light, time also slows down. These effects are not just theoretical curiosities. They are real, measurable phenomena that have been confirmed by countless experiments. They tell us that time is malleable, flexible, and intimately connected to the speed of light. As we begin this exploration, we invite you to set aside your everyday assumptions about time. Let go of the notion that time is a river flowing steadily from past to future. Instead, consider the possibility that time might be more like a symphony, with different parts of the universe playing at different tempos, all synchronized by the universal conductor that is the speed of light. The questions we will explore tonight are not just academic puzzles. They touch on the deepest mysteries of existence. If time is indeed an illusion created by the speed of light, What does this mean for our understanding of consciousness, memory, and the nature of being alive? How do we make sense of our subjective experience of duration, of waiting, of the feeling that time sometimes flies and sometimes crawls? Throughout history, humans have wondered about the nature of time. Ancient philosophers debated whether time was real or illusory. Mystics spoke of eternal moments that seemed to exist outside the normal flow of duration. Scientists have gradually uncovered the mathematical relationships that govern how time behaves under different conditions. Now, we stand at the threshold of a new understanding, one that might reveal time to be one of the most beautiful and profound illusions ever discovered. As we settle in for this cosmic journey, let the gentle rhythm of your breathing remind you of time's passage. Feel the steady beat of your heart marking moments. Notice how your thoughts flow from one to the next, creating your personal experience of duration. All of these familiar experiences of time may be about to take on new meaning as we explore the possibility that time itself is a creation of light, a cosmic magic trick performed by photons racing through the universe at their eternal, unchanging speed. To understand whether time might be an illusion created by light, we must first explore what time means to us and how we experience it in our daily lives. Time is perhaps the most intimate aspect of our existence, yet it remains one of the most mysterious. We feel it passing moment by moment, we organize our lives around it, and we measure it with incredible precision. But what exactly is this thing we call time? From the moment we wake up in the morning, time governs our experience. We check clocks, we follow schedules, we remember the past and anticipate the future. Our entire civilization is built around the shared understanding that time moves forward, that events happen in sequence, and that there is a meaningful difference between yesterday, today, and tomorrow. Yet despite this familiarity, time resists simple definition. The ancient Greeks had two different words for time. Chronos referred to the mechanical, measurable aspect of time, the kind we track with clocks and calendars. Kairos described the qualitative experience of time, those moments when time seems to slow down or speed up based on our emotional state or level of attention. Both aspects of time are real parts of our experience, and both may hold clues to understanding whether time is fundamental or constructed. Think about how we actually measure time. At its most basic level, we count repetitions. The rotation of the Earth gives us days. The orbit of the Earth around the Sun gives us years. The swinging of a pendulum gives us seconds and minutes. Even our most precise atomic clocks work by counting the vibrations of atoms. In every case, we are using one type of regular motion to measure duration and sequence. This raises a fascinating question. If all our measurements of time depend on motion, and if all motion happens at speeds that are ultimately limited by the speed of light, then perhaps our entire concept of time is built on a foundation of light speed limitations. The atoms in our clocks vibrate as their electrons move between energy levels, and these movements are governed by electromagnetic forces that propagate at the speed of light. Consider the biological clocks that exist within our own bodies. Our circadian rhythms, which regulate sleep and wakefulness, are synchronized to the cycle of day and night. This cycle exists because the Earth rotates, creating the regular alternation of light and darkness that has shaped life on our planet for billions of years. Even our heartbeat and breathing create rhythmic patterns that our brains use as internal timepieces. But here is where things become intriguing. All of these biological processes, from the firing of neurons to the chemical reactions in our cells, involve the movement of electrons and the propagation of electromagnetic signals. The speed at which these processes can occur is ultimately limited by how fast information can travel, which brings us back to the speed of light as a fundamental constraint. Our brains construct our sense of the present moment from information arriving through our senses. Light enters our eyes, sound waves reach our ears, and chemical signals activate our senses of smell and taste. All of this sensory information must be processed and integrated to create our conscious experience of now. But this integration takes time, and the speed at which it happens is limited by how fast signals can travel through our nervous system. Remarkably, our brains are constantly making predictions about the future to compensate for these processing delays. When you reach out to catch a ball, your brain must predict where the ball will be by the time your muscles respond to the command to move. This prediction is based on the assumption that the ball will continue following the laws of physics, laws that are themselves connected to the speed of light through the electromagnetic forces that hold matter together. The universality of time measurement across cultures suggests that our perception of temporal flow is rooted in something deeper than mere convention. Every human society has developed ways to track the passage of time, to record events in sequence, and to coordinate activities. This universal human need to measure and organize time hints that we are responding to something fundamental in the structure of reality itself. Yet different cultures have developed remarkably different concepts of what time actually is. Some view time as cyclical, with events repeating in great cosmic cycles. Others see time as linear, with a clear beginning, middle, and end. Some philosophies treat time as an illusion to be transcended, while others see it as the most basic aspect of existence. These diverse perspectives suggest that while the measurement of time may be universal, the interpretation of what time means is deeply influenced by human cognition and culture. Modern physics has revealed that time is far stranger than our everyday experience suggests. At the scale of fundamental particles, the equations that describe physical processes are often symmetric with respect to time. This means that mathematically, many physical processes could run equally well forward or backward in time. The arrow of time that we experience so clearly in our daily lives emerges from statistical properties of large collections of particles, not from the fundamental laws themselves. This emergence of temporal direction from timeless underlying laws is one of the great puzzles of physics. It suggests that our experience of time flowing from past to future might be a consequence of the particular way matter and energy are organized in our universe, rather than a fundamental property of reality itself. If time's arrow emerges from the collective behavior of matter and energy, and if matter and energy interact through fields that propagate at the speed of light, then once again we find ourselves contemplating the deep connection between light and time. The precision with which we can now measure time is truly extraordinary. Our best atomic clocks are accurate to 1 part in 10 to the 18th power, meaning they would not gain or lose a second over the entire age of the universe. This precision has allowed us to detect tiny variations in the flow of time due to gravitational effects and relative motion. These measurements confirm that time is not absolute, but is intimately connected to space, matter, and energy in ways that Einstein predicted over a century ago. As we push the boundaries of temporal measurement, we discover that time becomes increasingly mysterious. At the smallest scales of quantum mechanics, the very concept of time becomes problematic. Quantum events seem to happen without a clear temporal sequence, and the act of measurement appears to retroactively determine when events occurred. These quantum mysteries suggest that our classical notion of time flowing smoothly from past to future may be an approximation that breaks down when we look too closely at the fundamental level of reality. The question of whether time is real or illusory has profound implications for how we understand consciousness, memory, and personal identity. If time is indeed a construction, rather than a fundamental aspect of reality, then our sense of being continuous selves persisting through time might need to be reconsidered. Perhaps what we call the self is actually a pattern of information that creates the illusion of temporal continuity, much like how a river maintains its identity despite being composed of ever-changing water. Time is the thread that connects all moments, the stage upon which the drama of existence unfolds. But what if this stage is not what it appears to be? What if time itself is influenced by something far more fundamental, something as basic as the speed at which light travels through the vacuum of space? As we prepare to explore this possibility, we must be willing to question our most basic assumptions about the nature of reality and to follow the evidence wherever it leads, even if it challenges our most cherished beliefs about the nature of existence itself. In the vast theatre of the cosmos, there exists a speed that appears to be woven into the very fabric of reality itself. This speed is not just fast, it is the ultimate speed, the cosmic speed limit that nothing in the universe can exceed. It is the speed of light, and it travels at exactly 299,792,458 meters per second through the vacuum of space. This number is not arbitrary. It represents something profound about the structure of space and time themselves. To truly appreciate the significance of light speed, we must first understand what makes it so special. Light is not simply one type of wave among many. It is the visible manifestation of electromagnetic radiation, a fundamental force that shapes the behavior of matter and energy throughout the universe. When we see light, we are witnessing the propagation of electromagnetic fields through space, fields that carry information about the objects that emitted them. The speed at which these electromagnetic fields propagate appears to be built into the geometry of space and time. It is not that light chooses to travel at this particular speed, but rather that this speed represents a fundamental property of the space-time through which light moves. In empty space, devoid of matter and energy, electromagnetic waves naturally propagate at this cosmic speed limit. What makes this speed truly remarkable is its constancy. No matter how fast you are moving, when you measure the speed of light, you always get the same answer. If you are standing still and measure light passing by, it moves at the speed of light. If you are traveling in a spacecraft at half the speed of light and measure light passing by, it still moves at the speed of light relative to you. This seemingly impossible fact revolutionized our understanding of space and time. This constancy of light speed forced scientists to abandon the common sense notion that space and time are separate, absolute entities. Instead, space and time became understood as different aspects of a single, unified space-time continuum. The speed of light serves as the conversion factor between space and time, determining how measurements of distance and duration are related to each other. Think of space-time as a vast fabric stretching throughout the universe. Light travels through this fabric at its natural speed, which is determined by the intrinsic properties of the fabric itself. Just as the speed of sound in air is determined by the properties of air molecules, the speed of light in space-time is determined by the fundamental structure of space-time. But unlike sound, which needs a medium like air to propagate, light travels through empty space itself. The implications of this are staggering. Every event in the universe, from the collision of distant galaxies to the firing of a single neuron in your brain, is connected to every other event through the propagation of electromagnetic fields at light speed. Information about what is happening here cannot reach there instantaneously. There is always a delay, always a gap between cause and effect that is determined by the distance involved and the speed of light. This cosmic speed limit creates what physicists call light cones. Imagine every event in space-time as the tip of a cone expanding outward at the speed of light. Everything inside the cone represents regions of space-time that can be causally connected to the original event. Everything outside the cone represents regions that cannot yet have received information about the event. The boundary of the cone, expanding at light speed, represents the frontier of causal influence. These light cones fundamentally shape the structure of causality in our universe. They determine which events can influence which other events, and they create a natural ordering of cause and effect. But perhaps most intriguingly, they also create regions of space-time that are causally disconnected from each other. Events happening simultaneously in different parts of the universe may have no causal connection whatsoever, existing in a kind of temporal isolation from each other. The speed of light also determines the fundamental scales of physics. At the smallest level, it sets the scale for quantum mechanics through Planck's constant, which has units that involve the speed of light. At the largest level, it determines the size of the observable universe by limiting how far we can see based on the age of the universe and the time light has had to travel to reach us. In our everyday experience, light speed seems instantaneous because the distances involved are so small compared to the cosmic scale. When you turn on a light switch, the room appears to illuminate immediately. But even in this simple act, there are tiny delays as electromagnetic signals propagate through the wires and as light travels from the bulb to your eyes. These delays are imperceptible to our senses, but they are real and they accumulate over cosmic distances. Consider what happens when you look at the stars. The light from the nearest star beyond our Sun, Proxima Centauri, has traveled for over 4 years to reach your eyes. When you see this star, you are literally looking into the past. The star you see is not the star as it exists now, but as it existed 4 years ago. If that star suddenly disappeared, you would not know about it for over 4 years. This effect becomes even more dramatic when we look at distant galaxies. Some of the galaxies we observe are so far away that we see them as they were billions of years ago, when the universe was young and very different from how it is today. In a very real sense, telescopes are time machines, allowing us to observe the history of the universe by collecting light that has been traveling toward us across cosmic distances. The finite speed of light creates a fundamental asymmetry in our knowledge of the universe. We can know about the past by observing light that has reached us, but we cannot know about distant events happening now until their light has had time to reach us. This creates a kind of cosmic horizon beyond which we cannot see, not because there is nothing there, but because light from those regions has not yet had time to reach us. Even more remarkably, the expansion of the universe means that some regions of space are moving away from us faster than light can travel toward us. Light from these regions will never reach us, creating permanent blind spots in our cosmic vision. These regions are not just currently invisible to us, they are fundamentally and forever unobservable. The speed of light also plays a crucial role in determining the arrow of time. The fact that light travels at a finite speed means that information propagates through the universe in a specific direction, from past to future. This creates a natural ordering of events and helps establish the direction of causality that we experience as the flow of time. Within Einstein's theory of special relativity, the speed of light emerges as the speed of causality itself. It is not just the speed at which light happens to travel, but the maximum speed at which any cause can produce an effect. This makes light speed fundamental to the very concept of cause and effect, and therefore to our understanding of how events unfold in time. As we contemplate the role of light speed in shaping our experience of time, we begin to see that time and light are not separate phenomena, but are intimately connected aspects of a deeper reality. The speed of light does not just affect how we observe time, it may actually determine the very nature of temporal experience itself. If our perception of time is built upon the propagation of information at light speed, then understanding light becomes essential to understanding time. But the story of light speed goes even deeper than these cosmic considerations. The speed of light is intimately connected to the fundamental constants that govern all physical processes in our universe. It appears in the equations that describe how atoms emit and absorb energy, how chemical bonds form and break, and how the forces of nature propagate through space. In a very real sense, the speed of light is embedded in the machinery of reality itself. When we examine the microscopic world of atoms and molecules, we find that all the processes that create our everyday experience depend on electromagnetic interactions that propagate at light speed. The electrons in your brain that create your thoughts, the chemical reactions in your muscles that allow you to move, the photosynthesis in plants that sustains life on Earth. All of these processes are governed by electromagnetic forces that travel at the speed of light. This creates a fascinating possibility. If our entire physical existence, including our brains and nervous systems, operates through processes that are ultimately limited by light speed, then perhaps our perception of time is fundamentally shaped by this cosmic speed limit. We may be like characters in a cosmic movie, experiencing reality at 24 frames per second. But instead of frames per second, we experience reality at light speed interactions per moment. The relationship between light speed and the structure of matter runs even deeper. According to quantum field theory, even empty space is not truly empty, but is filled with quantum fields that fluctuate at the smallest scales. These quantum fluctuations involve virtual particles that pop into and out of existence, and the rate at which they do so is governed by fundamental constants that include the speed of light. In this view, the vacuum of space itself is a dynamic medium whose properties determine the speed at which light propagates. Consider the profound implications of this. If space itself is not a passive backdrop, but an active participant in physical processes, then the speed of light may be telling us something fundamental about the nature of space and time. The speed of light might not be simply a speed limit imposed on matter and energy moving through space, but rather a reflection of the intrinsic temporal structure of space itself. This perspective suggests that time and space are not separate entities that happen to be connected by the speed of light, but rather that the speed of light reveals the fundamental unity of space and time. In this view, what we call space is actually the spatial aspect of space-time, and what we call time is the temporal aspect of the same underlying reality. The speed of light is the conversion factor that allows us to translate between spatial and temporal measurements of this unified space-time. The constancy of light speed across all reference frames was one of the most shocking discoveries in the history of physics. It violates our everyday intuitions about how speeds should add together. If you throw a ball forward from a moving train, the ball's speed relative to the ground is the sum of the train's speed and your throwing speed. But light does not behave this way. No matter how fast the source of light is moving, the light always travels at the same speed relative to any observer. This strange behavior forced physicists to realize that space and time themselves must be flexible. As objects approach the speed of light, space contracts and time dilates in precisely the right amounts to ensure that light speed remains constant for all observers. This is not simply a curious mathematical trick, but a fundamental feature of the geometry of space-time itself. The flexibility of space and time revealed by the constancy of light speed has profound implications for our understanding of simultaneity. Events that appear to happen at the same time for one observer may happen at different times for another observer moving at a different speed. There is no universal now that extends across the entire universe. Instead, simultaneity is relative, determined by the observer's motion through space-time. This relativity of simultaneity means that the present moment is not a cosmic slice through space-time that divides past from future everywhere at once. Instead, each observer carries their own definition of now, their own slice through space-time that defines what they consider to be simultaneous events. These different definitions of now are all equally valid, and they are all connected by the geometry of space-time and the constancy of light speed. The implications extend beyond abstract physics into the realm of consciousness and experience. If our brains construct our sense of the present moment from sensory information that arrives at light speed, and if simultaneity itself is relative, then our conscious experience of now may be a kind of construction, a brain-generated illusion of temporal unity imposed on information that actually arrives at different times and from different distances. Think about what happens when you experience a sunset. The light from the sun left its surface about 8 minutes ago. The light reflected from the clouds left them fractions of a second ago. The sounds of birds singing reach your ears at the much slower speed of sound. Your brain somehow weaves all of this temporally displaced information together into a unified experience of this moment. But is this moment real? Or is it a construction created by your nervous system? The speed of light also determines the fundamental scale of quantum mechanics through its appearance in Planck's constant. At the Planck scale, which is determined by the speed of light, quantum gravity effects become important, and our classical notions of space and time may break down entirely. Some theories suggest that at this scale, space-time itself becomes quantized, made up of discrete units rather than being smooth and continuous. If space-time is indeed quantized at the Planck scale, then time itself may be made up of discrete moments, like frames in a cosmic movie. The duration of each Planck time unit is approximately 10 to the negative 43 seconds, an almost unimaginably brief interval. If time is indeed quantized at this scale, then the smooth flow of time that we experience may be an approximation, valid only at scales much larger than the Planck scale. The relationship between light speed and the quantum nature of reality extends to the phenomenon of quantum entanglement, where particles can be instantly correlated across arbitrary distances. This appears to violate the speed of light limit, but careful analysis reveals that no information actually travels faster than light. Instead, entanglement seems to reveal something deeper about the non-local nature of quantum reality, something that transcends our classical notions of space and time while still respecting the cosmic speed limit. These quantum mysteries hint that the relationship between light, space, and time may be even stranger than Einstein's relativity suggests. In the quantum realm, the very concepts of position and time become uncertain, and the act of measurement seems to play a fundamental role in determining physical reality. If consciousness and measurement are intimately connected, then the speed of light may not only determine the structure of physical space-time, but may also shape the emergence of conscious experience itself. The cosmic speed limit imposed by light creates a universe where simultaneity is relative, where the present moment depends on your frame of reference, and where the flow of time itself can vary depending on your motion and location. But more than this, it creates a universe where consciousness itself may be shaped by the fundamental speed at which information can propagate. These revelations suggest that time, as we experience it, may indeed be shaped by the fundamental properties of light and its propagation through space-time. As we delve deeper into these connections, we move closer to understanding whether time might truly be an illusion created by the speed of light itself. Imagine embarking on a journey to the stars, traveling at speeds approaching the ultimate cosmic limit. As your spacecraft accelerates closer and closer to the speed of light, something extraordinary begins to happen. Time itself starts to slow down around you. Not just your perception of time, but the actual rate at which time flows. This is not science fiction, but one of the most thoroughly tested and verified predictions of Einstein's theory of relativity. It is called time dilation, and it reveals that time is far more flexible and mysterious than our everyday experience suggests. Time dilation represents one of the most profound departures from our intuitive understanding of reality. In our daily lives, We assume that time flows at the same rate for everyone, everywhere. We synchronize our clocks, coordinate our schedules, and assume that when we say it is 3 o'clock, it is 3 o'clock for everyone in the universe. But relativity tells us this assumption is fundamentally wrong. Time does not flow at a universal rate. Instead, the passage of time depends on how fast you are moving and where you are located in gravitational fields. The mathematics of time dilation are precise and unforgiving. As an object approaches the speed of light, time slows down according to a specific formula that involves the speed of the object and the speed of light. When an object moves at 90% of light speed, time runs about 43% slower for that object compared to a stationary observer. At 99% of light speed, time runs about 7 times slower. At 99.9% of light speed, time runs about 22 times slower. These numbers are not approximations or estimates. They are exact predictions that have been confirmed by countless experiments. Particles in accelerators regularly approach these speeds, and their behavior precisely matches the predictions of relativity. Atomic clocks flown on airplanes run slightly slower than identical clocks on the ground. GPS satellites must correct for time dilation effects to maintain their accuracy. Time dilation is not a theoretical curiosity, but a practical reality that affects technologies we use every day. The most famous illustration of time dilation is the twin paradox. Imagine identical twins, Alice and Bob, both 20 years old. Alice remains on Earth while Bob travels to a distant star at 99% of the speed of light. The journey takes 20 years from Alice's perspective on Earth. During this time, Alice ages 20 years and is now 40 years old. But for Bob, traveling at nearly light speed, time has been running about 7 times slower. From his perspective, the journey took less than 3 years. When Bob returns to Earth, he is only about 23 years old, while his twin sister Alice is 40 years old. This scenario seems to violate our basic intuitions about the nature of time and aging. How can two people, starting at the same age, end up with different ages simply because one traveled at high speed? The key insight is that time itself is not absolute. There is no universal clock ticking away in the background of the universe. Instead, each observer carries their own proper time, determined by their motion through space-time. The twin paradox reveals something profound about the relationship between motion and time. The faster you move through space, the slower you move through time. This trade-off between spatial motion and temporal motion is built into the geometry of space-time itself. You can think of it as a cosmic speed limit that applies not just to motion through space, but to motion through space-time as a whole. Every object in the universe moves through space-time at exactly the speed of light. This might seem strange, since most objects move much slower than light speed through space. But the key insight is that motion through space-time includes both motion through space and motion through time. When you are sitting still in space, you are moving through time at the maximum rate. As you begin to move through space, you trade some of your motion through time for motion through space. The faster you move through space, the slower you move through time. This perspective reveals that time dilation is not an effect that happens to time, but rather a consequence of the fundamental geometry of space-time. Time does not slow down because of some mysterious force or field. Instead, time dilation emerges naturally from the way space and time are woven together into a unified space-time continuum. The speed of light serves as the fundamental metric that determines how spatial motion trades off against temporal motion. The implications of time dilation extend far beyond space travel scenarios. Every time you move, even when walking down the street, you experience a tiny amount of time dilation. The effect is far too small to notice in everyday life, but it is real and measurable with sufficiently precise instruments. Professional athletes running at top speed age infinitesimally less than spectators watching from the stands. Passengers on high-speed trains experience slightly less time than people on the platform. These effects become more pronounced as speeds increase. Particles in cosmic rays, traveling at speeds very close to light speed, experience extreme time dilation. From our perspective on Earth, these particles live much longer than they should based on their known decay rates. From the particles' perspective, they decay at their normal rate, but the journey through Earth's atmosphere takes much less time due to length contraction, the spatial companion to time dilation. Time dilation also occurs in gravitational fields, an effect known as gravitational time dilation. Clocks run slower in stronger gravitational fields and faster in weaker ones. A clock at sea level runs slightly slower than an identical clock on a mountaintop. This effect has been measured with atomic clocks and is another confirmation of Einstein's predictions. The global positioning system must account for both velocity-based time dilation and gravitational time dilation to maintain accuracy. The connection between gravity and time dilation reveals something deep about the nature of gravity itself. Einstein realized that gravity is not a force in the traditional sense, but rather a manifestation of the curvature of space-time. Massive objects like stars and planets warp the fabric of space-time, and this warping affects the flow of time. Near massive objects, time runs slower, not because of some gravitational force acting on clocks, but because space-time itself is curved in such a way that temporal measurements are affected. This geometric understanding of time dilation suggests that time is not a separate entity that can be affected by external forces, but rather an integral aspect of the space-time geometry. Time dilation does not happen to time from the outside, but rather emerges from the intrinsic properties of space-time itself. This perspective hints that our everyday notion of time as a flowing river may be fundamentally misguided. The practical applications of time dilation extend into cutting-edge physics research. Particle accelerators routinely accelerate particles to speeds where time dilation becomes significant. The lifetimes of unstable particles are extended by time dilation, allowing researchers to study particles that would otherwise decay too quickly to observe. Time dilation is not just a theoretical prediction, but a practical tool used in experimental physics. The phenomenon of time dilation also raises profound questions about the nature of consciousness and subjective experience. If Bob, in our twin paradox, experiences less time during his high-speed journey, does he also experience fewer conscious moments? Does his subjective experience of the journey differ from what we might expect based on the duration measured by Earth-based observers? These questions touch on deep mysteries about the relationship between physical time and conscious experience. Some researchers have speculated that consciousness itself might be related to information processing rates in the brain, and that these rates might be affected by time dilation. If true, this could mean that subjective experience is intimately connected to the flow of physical time in ways we are only beginning to understand. The flexibility of time revealed by relativity might extend to the flexibility of conscious experience itself. The study of time dilation has also led to insights about the fundamental nature of measurement and observation. The fact that different observers can measure different time intervals for the same events challenges our assumptions about objective reality. It suggests that measurement is not simply a passive recording of pre-existing facts, but rather an active process that depends on the relationship between the observer and the observed. This observer dependence of temporal measurements has philosophical implications that extend beyond physics. If time intervals depend on the observer's state of motion, then perhaps other aspects of reality are also observer-dependent in ways we have not yet discovered. The flexibility of time might be just one example of a more general principle that reality is fundamentally relational rather than absolute. As we contemplate the implications of time dilation, we begin to see that time is far more malleable than our everyday experience suggests. The rigid, universal time of common sense gives way to a flexible, observer-dependent time that responds to motion and gravity. This flexibility hints that time might indeed be a construction rather than a fundamental aspect of reality, a construction that depends on the speed of light and the geometry of space-time. The phenomenon of time dilation reveals that the speed of light is not just a speed limit for motion through space, but a fundamental constant that determines how motion through space trades off against motion through time. This trade-off suggests that space and time are not separate entities, but different aspects of a unified space-time, and that the speed of light serves as the fundamental metric that governs the relationships between spatial and temporal measurements. If our experience of time is built upon processes that occur at rates limited by the speed of light, and if time itself can slow down when we approach light speed, then perhaps our entire temporal experience is shaped by this cosmic speed limit. Time dilation shows us that time is not the absolute universal flow we imagine it to be, but rather a flexible aspect of space-time that responds to our motion and location. This flexibility brings us one step closer to understanding whether time might truly be an illusion created by the fundamental properties of light and space-time. In the quiet moments of contemplation, we often assume that somewhere in the vast universe there exists a cosmic clock, ticking away the moments that define a universal now. We imagine that when we say it is midnight here on Earth, there is a corresponding moment of midnight that extends across the entire cosmos, slicing through space and time to define what is happening now everywhere at once. This intuitive belief in a universal present moment seems so natural, so obvious, that questioning it feels almost absurd. Yet Einstein's theory of relativity tells us that this cosmic now is nothing more than an illusion, a comforting fiction that has no basis in the actual structure of space-time. The relativity of simultaneity is perhaps the most mind-bending consequence of Einstein's insights into the nature of space and time. It tells us that events which appear to happen at the same time for one observer may occur at completely different times for another observer moving at a different velocity. There is no absolute simultaneity, no universal moment that all observers can agree represents the present. Instead, each observer carries their own definition of now, their own slice through the four-dimensional fabric of space-time. To understand how this extraordinary situation arises, imagine two observers, Sarah and Michael, moving relative to each other at high speed. Sarah is traveling in a spacecraft while Michael remains on a space station. At the moment when Sarah passes by Michael's location, both observers decide to synchronize their definition of now across the universe. Using light signals, they each determine which distant events they consider to be happening simultaneously with their meeting. Because light travels at a finite speed, both observers must account for the time it takes light to travel from distant events to their location. But here is where things become strange. Because Sarah and Michael are moving relative to each other, they will disagree about which distant events are simultaneous with their meeting. Events that Sarah considers to be happening now may have already happened from Michael's perspective, or may not yet have occurred. The faster their relative motion, the greater their disagreement about simultaneity. This disagreement is not due to measurement errors or limitations in their equipment. It is a fundamental feature of space-time itself. The geometry of space-time is such that simultaneity depends on the observer's state of motion. There is no way to define a universal now that all observers will agree upon. Each observer's definition of simultaneity is equally valid, and the differences between them reveal something profound about the nature of time itself. The implications of this relativity of simultaneity extend far beyond abstract thought experiments. Consider what it means for our understanding of causality and free will. If two events are simultaneous for one observer, but sequential for another, which version represents reality? If an event that seems to be in your future from one perspective has already happened from another perspective, what does this mean for the idea that the future is open and undetermined? These questions become even more puzzling when we consider the block universe interpretation of relativity. According to this view, all events in space-time exist equally, forming a four-dimensional block in which past, present, and future are simply different locations along the time dimension. From this perspective, the flow of time and the special status of the present moment are illusions created by our consciousness as it moves through the block universe. In the block universe, your birth, your current moment of reading these words, and your eventual death all exist simultaneously as different locations in the four-dimensional space-time continuum. The feeling that only the present moment is real and that the past is gone while the future is yet to come emerges from the particular way consciousness samples the block universe. Time does not flow. Consciousness flows through time, creating the subjective experience of temporal passage. This perspective radically challenges our everyday understanding of existence and reality. If all moments exist equally, then in what sense do we live in time rather than simply existing across time? If the past and future are as real as the present, then what gives the present moment its apparent special significance? These questions touch on some of the deepest mysteries of consciousness and the nature of subjective experience. The relativity of simultaneity also has practical implications for our understanding of information and communication across cosmic distances. Because simultaneity is relative, there is no universal way to define what information is available now at different locations in the universe. Information that seems currently available from one perspective may not yet exist from another perspective. This creates fundamental limits on how information can be coordinated across space. Consider the challenge of coordinating activities across a galactic civilization. If different parts of the galaxy are moving relative to each other, they will disagree about simultaneity and therefore about what information is currently available. Decisions that seem to be based on current information from one perspective may be based on outdated or not yet available information from another perspective. The relativity of simultaneity creates fundamental challenges for any attempt to create a unified, synchronized galactic society. These coordination challenges extend to our understanding of physical laws and causality. If simultaneity is relative, then the order in which cause and effect occur may also be relative. Events that appear to have a clear causal relationship from one perspective may appear uncorrelated or even reverse correlated from another perspective. This does not violate causality, but it does mean that causal relationships must be understood within the context of specific reference frames. The speed of light plays a crucial role in determining the relativity of simultaneity. The faster light travels, the less significant the disagreements about simultaneity become. If light traveled infinitely fast, all observers would agree about simultaneity, and there would be a universal now. But because light travels at a finite speed, information about distant events takes time to propagate, and this propagation delay depends on the observer's motion in a way that creates disagreements about simultaneity. This connection between light speed and simultaneity suggests that our experience of a universal present moment may be an artifact of the finite speed of light. If our brains construct our sense of now from sensory information that propagates at light speed, then perhaps the feeling of a universal present is actually a construction created by the way our nervous systems process light speed limited information. The relativity of simultaneity also reveals something deep about the nature of space and time themselves. In pre-relativistic physics, space and time were thought to be separate, absolute entities. Space provided the stage for events, and time provided the universal clock that measured when events occurred. But relativity shows us that space and time are intimately connected aspects of a unified space-time. and that measurements of both space and time depend on the observer's state of motion. This unification of space and time through the relativity of simultaneity suggests that our everyday distinctions between spatial and temporal relationships may be artifacts of our particular perspective, rather than fundamental features of reality. From the perspective of space-time as a whole, all events exist in a four-dimensional continuum, where the distinctions between here and there, now and then, are matters of perspective rather than absolute facts. The philosophical implications of the relativity of simultaneity extend to questions about personal identity and the continuity of consciousness across time. If there is no universal now that defines a single present moment, then in what sense do we exist as continuous beings persisting through time? Perhaps what we call personal identity is actually a construction that emerges from the way consciousness samples the four-dimensional space-time continuum. Different philosophical traditions have approached these questions in various ways. Some Eastern philosophies have long taught that the flow of time and the distinctness of moments are illusions to be transcended through spiritual practice. Some Western philosophers have argued that temporal experience is fundamental to consciousness and cannot be reduced to mere physical processes. The relativity of simultaneity adds a new dimension to these ancient debates. The challenges posed by the relativity of simultaneity extend to our understanding of knowledge and truth. If different observers disagree about which events are simultaneous, then they may also disagree about what facts are currently true. This does not mean that truth is arbitrary or that all perspectives are equally correct, but it does mean that truth must be understood within the context of specific reference frames and observational perspectives. Modern physics continues to grapple with the implications of the relativity of simultaneity. Quantum mechanics introduces additional complications through phenomena like quantum entanglement, where particles can be instantly correlated across arbitrary distances. These quantum correlations seem to violate the spirit of relativity by suggesting that some aspects of reality transcend the speed of light limitations that create the relativity of simultaneity. The tension between quantum mechanics and relativity in the realm of simultaneity remains one of the great unsolved problems in physics. Some interpretations of quantum mechanics suggest that the relativity of simultaneity may be incomplete, and that there may be deeper levels of reality where a universal now does exist. Other interpretations embrace the relativity of simultaneity and seek to understand quantum phenomena within this framework. As we contemplate the absence of a universal now, we are forced to reconsider our most basic assumptions about the nature of time and reality. The comforting notion of a cosmic present moment that unifies all of existence gives way to a more complex picture, where now is always relative, always dependent on perspective, always limited by the speed at which information can propagate through space-time. This relativity of the present moment brings us closer to understanding how time might be an illusion created by the speed of light. If simultaneity depends on light speed, and if our sense of now is constructed from light speed limited information, then perhaps the entire framework of temporal experience is built upon the foundation of light's finite propagation speed. The universal now that seems so real and immediate may be nothing more than a beautiful illusion, a cosmic mirage created by the interplay between consciousness and the speed of light. Imagine the universe as a vast, invisible fabric stretching infinitely in all directions. This fabric is not made of threads or fibers that we can touch, but rather of something far more fundamental. It is woven from the very essence of space and time themselves, creating a unified tapestry that physicists call space-time. This cosmic fabric provides the stage upon which all the drama of existence unfolds, from the dance of subatomic particles to the stately waltz of galaxies across the cosmos. And threading through this fabric, like golden strands that reveal its hidden structure, travels light at its eternal, unchanging speed. To truly understand how light shapes our experience of time, we must first appreciate the profound revolution in thinking that led to the concept of space-time. Before Einstein, space and time seemed to be separate, independent aspects of reality. Space was the three-dimensional arena where objects moved and interacted. Time was the universal clock that measured the duration and sequence of events. These two aspects of reality appeared to be fundamentally different in nature, as distinct as matter and energy, as separate as cause and effect. But Einstein's insights revealed that this separation was an illusion, a limitation of our everyday perspective, rather than a fundamental truth about reality. Space and time are not separate entities, but are woven together into a single, unified fabric. What we perceive as space is actually the spatial dimension of space-time. What we experience as time is actually the temporal dimension of the same underlying reality. The speed of light serves as the fundamental constant that determines how these dimensions relate to each other. This unification of space and time into space-time represents one of the most profound conceptual revolutions in human history. It means that every event in the universe must be understood, not just in terms of where it happens, but when it happens. Location in space-time requires 4 coordinates, 3 for space and 1 for time. Every physical process, from the beating of your heart to the explosion of distant supernovas, unfolds within this 4-dimensional space-time continuum. The fabric of space-time is not rigid and unchanging like the stage in a theatre. Instead, it is dynamic and responsive, capable of being stretched, compressed, twisted, and curved by the presence of matter and energy. Massive objects like stars and planets create depressions in the space-time fabric, much like a heavy ball creates a depression when placed on a stretched rubber sheet. These depressions in space-time are what we experience as gravitational fields. Light travels through this curved space-time fabric, and its path reveals the curvature. When light passes near a massive object, it follows the curves in space-time, appearing to bend from the perspective of a distant observer. This bending of light was one of the first experimental confirmations of Einstein's theory of general relativity. It demonstrated that space and time are not just mathematical abstractions, but have physical reality that can be measured and observed. The curvature of space-time also affects the flow of time itself. In regions where space-time is more curved, time runs slower relative to regions where space-time is less curved. This gravitational time dilation is not just a theoretical prediction, but a measurable effect that must be accounted for in technologies like GPS satellites. The satellites orbit Earth in a weaker gravitational field than exists at Earth's surface, so their clocks run slightly faster and must be corrected to maintain accuracy. Understanding space-time as a fabric helps us visualize how light and time are interconnected. Light always travels along the straightest possible paths through space-time, paths that mathematicians call geodesics. In flat space-time, these geodesics are straight lines, but in curved space-time, geodesics follow the curves of the fabric itself. Light does not choose to follow these curved paths, it simply follows the geometry of space-time, much like a marble rolling on a curved surface naturally follows the contours of that surface. The speed of light serves as the fundamental metric of space-time, determining how spatial and temporal measurements relate to each other. This metric is built into the very structure of space-time itself. Just as the properties of a fabric determine how it responds to stretching and bending, the metric of space-time determines how space and time measurements transform when observed from different reference frames. This deep connection between light and the structure of space-time suggests that our experience of time may be fundamentally shaped by the way light propagates through the cosmic fabric. Every process that creates our temporal experience, from the firing of neurons in our brains to the atomic vibrations in our clocks, involves the propagation of electromagnetic fields at light speed. These fields follow the geodesics of space-time. carrying information about events from one location to another. The fabric of space-time also provides the medium through which all forces, except gravity, propagate. The electromagnetic force, which governs the behavior of atoms and molecules, travels through space-time at light speed. The strong and weak nuclear forces which govern the behavior of atomic nuclei also propagate at light speed over their limited ranges. Even gravity, which curves space-time itself, propagates changes in that curvature at light speed through gravitational waves. This means that all the forces that shape matter and energy in our universe are intimately connected to light speed and the structure of space-time. The atoms in your body, the molecules in the air you breathe, the chemical reactions that power your cells, all of these processes depend on forces that propagate at light speed through the space-time fabric. In a very real sense, your entire physical existence is sustained by light speed interactions weaving through the cosmic fabric. The quantum nature of reality adds another layer of complexity to our understanding of the space-time fabric. At the smallest scales, quantum fluctuations cause the fabric itself to fluctuate, creating a kind of quantum foam where the smooth geometry of classical space-time breaks down. These quantum fluctuations involve virtual particles that appear and disappear in accordance with the uncertainty principle, and the rate at which they do so is governed by fundamental constants that include the speed of light. At the Planck scale, which is determined by the speed of light along with other fundamental constants, the classical notion of space-time as a smooth fabric may no longer apply. Some theories suggest that at this scale, space-time itself becomes quantized, made up of discrete units rather than being continuous. If this is true, then the fabric metaphor may be more literal than we imagine, with space-time actually composed of fundamental units woven together like the threads in a cosmic tapestry. The fabric of space-time also provides the stage for some of the most exotic phenomena in the universe. Black holes represent regions where the fabric is curved so extremely that not even light can escape. At the event horizon of a black hole, the curvature of space-time becomes so severe that time itself appears to stop from the perspective of a distant observer. Inside the black hole, the fabric may be torn or twisted in ways that challenge our understanding of space and time. Gravitational waves represent ripples in the space-time fabric itself, propagating outward from accelerating masses at light speed. These waves stretch and compress space and time as they pass, creating tiny oscillations that can be detected by sensitive instruments. The detection of gravitational waves has opened a new window into the universe, allowing us to observe cosmic events through their effects on the space-time fabric, rather than through electromagnetic radiation. The expansion of the universe represents a stretching of the space-time fabric on the largest scales. As space expands, it carries galaxies along with it, creating the cosmic recession that we observe as the redshift of distant galaxies. This expansion affects the propagation of light across cosmic distances, creating effects like cosmological redshift that reveal the dynamic nature of space-time itself. Dark energy, the mysterious force that appears to be accelerating the expansion of the universe, may represent a property of the space-time fabric itself. Rather than being a substance or field that fills space, dark energy might be an intrinsic property of space-time that causes it to expand at an accelerating rate. This would mean that the fabric of reality itself has properties that we are only beginning to understand. The fabric of space-time also plays a crucial role in our understanding of cosmology and the origin of the universe. The Big Bang represents not just an explosion in space, but an expansion of space itself. The space-time fabric came into existence at the moment of the Big Bang and has been expanding ever since. This means that space and time themselves have a history, a beginning, and possibly an end. The study of space-time has revealed that what we think of as empty space is actually a dynamic, active medium filled with quantum fields and virtual particles. The vacuum of space is not empty, but is the lowest energy state of quantum fields that permeate space-time. These fields interact with matter and energy in ways that affect the propagation of light and the flow of time. Understanding space-time as a fabric woven from space and time helps us appreciate how deeply light is connected to the structure of reality itself. Light does not simply travel through space and time, it reveals the geometry of space-time and carries information about that geometry from one location to another. The speed of light is not just a speed limit for motion through space, but a fundamental property of the space-time fabric that determines how space and time relate to each other. As we contemplate the fabric of space-time and light's role in revealing its structure, we begin to see how our experience of time might emerge from the way information propagates through this cosmic medium. The temporal relationships we observe, the causal connections we infer, the sequence of events we experience, all of these aspects of temporal reality may be shaped by the way light threads through the space-time fabric, carrying information at its unchanging speed and revealing the hidden geometry of the universe. The fabric of space-time provides the foundation for all physical processes, and light serves as both the revealer of that fabric structure and the carrier of information about events within it. This deep interconnection between light, space-time, and temporal experience suggests that time itself may be not a fundamental aspect of reality, but rather an emergent property that arises from the way consciousness interacts with light-speed limited information propagating through the cosmic fabric. In this view, time becomes not the stage upon which reality unfolds, but rather a beautiful illusion created by the interplay between awareness and the speed of light, weaving through the infinite tapestry of space-time. In the depths of space, light travels with unwavering determination, carrying its precious cargo of information across the cosmic void at exactly 299,792,458 meters per second. This speed is not merely fast, it is the speed at which reality itself unfolds, the rate at which cause becomes effect, the pace at which the universe reveals its secrets to those who wait patiently for photons to complete their journeys. But what if this cosmic speed limit is not just a constraint on how fast things can move, but the very foundation upon which our experience of time is built? The flow of time, that most intimate and immediate aspect of our existence, may be nothing more than the subjective experience of living in a universe where information cannot travel faster than light. Every moment of consciousness, every heartbeat, every thought that crosses your mind depends on countless processes that are ultimately limited by how quickly electromagnetic signals can propagate through space. From the firing of neurons in your brain to the chemical reactions in your cells, from the vibrations of atoms in solid matter to the propagation of forces between particles, everything that creates your experience of temporal flow is constrained by the cosmic speed limit. Consider what happens when you experience the flow of time. Your brain constructs each moment of consciousness by integrating information from your senses, your memories, and your internal bodily processes. This integration requires signals to travel between different parts of your nervous system, and these signals move at speeds much slower than light, but still subject to the same fundamental constraints. The temporal coherence of consciousness, the feeling that your thoughts and perceptions happen in a coordinated sequence, emerges from the synchronization of countless light-speed limited processes. But the relationship between light speed and temporal flow goes deeper than the mechanics of neural processing. The very concept of sequence, of one event following another, depends on the propagation of causal influences at finite speed. If information could travel instantaneously, cause and effect would be simultaneous, and the universe would exist in a kind of eternal, unchanging now, where all events happen at once. It is the finite speed of light that creates the temporal gaps between cause and effect, the delays that allow us to perceive sequence and change. Imagine, for a moment, what would happen if the speed of light were different. If light traveled much faster than it actually does, the delays between cause and effect would be smaller, and the universe would seem more tightly connected in time. Events that now seem separate and sequential might appear to happen simultaneously. The flow of time might feel more rushed, more compressed, as information raced around the universe at ever-increasing speeds. On the other hand, if light traveled much slower than it actually does, the delays between cause and effect would be much longer. The universe would seem more stretched out in time, with greater gaps between events. The flow of time might feel more leisurely, more expanded, as information crawled slowly from one location to another. In such a universe, the present moment might feel more isolated, more cut off from distant events. These thought experiments suggest that our experience of temporal flow is intimately connected to the actual value of the speed of light in our universe. The particular rate at which time seems to flow may not be an absolute property of time itself, but rather a consequence of the specific speed at which information propagates through space-time. If this is true, then the flow of time is not fundamental, but is instead an emergent property that arises from the information processing limitations imposed by light speed. The finite speed of light also creates what physicists call the light cone structure of space-time. Every event exists at the tip of two cones, one extending into the past and one extending into the future. The past light cone contains all the events that could have causally influenced the present event, while the future light cone contains all the events that the present event could causally influence. The boundaries of these cones, expanding at light speed, define the limits of causal connection. This light cone structure may be the geometric foundation of temporal experience. Our sense of past, present, and future may correspond to our position within these light cones. The past consists of events within our past light cone, events whose influence could have reached us. The future consists of events within our future light cone, events that we could potentially influence. The present is the narrow interface between these two cones, the ever-changing boundary where past influences converge and future possibilities emerge. But here is where the story becomes even more intriguing. The light cones that define causal structure are not the same for all observers. Observers moving at different velocities have different light cone structures, different definitions of past and future, different boundaries between what has happened and what is yet to come. This means that the flow of time itself is observer-dependent, shaped by motion through space-time in ways that reflect the fundamental role of light speed in defining temporal relationships. The observer dependence of temporal flow raises profound questions about the nature of time itself. If different observers experience different flows of time, which flow represents the true nature of temporal passage? Or perhaps the question itself is misguided, and there is no single correct flow of time, but rather as many different temporal flows as there are observers. In this view, time does not flow in any absolute sense, but rather consciousness flows through space-time, creating the subjective experience of temporal passage. The relationship between light speed and temporal flow also appears in the quantum realm, where the uncertainty principle creates fundamental limits on how precisely we can know both the position and momentum of particles. This uncertainty is related to the wave nature of matter, and the speed at which these matter waves propagate is connected to the speed of light through the fundamental constants of quantum mechanics. The quantum fuzziness that prevents us from knowing exact positions and momenta may be another manifestation of the light speed limitations that shape temporal experience. At the smaller scales of space and time, near the Planck length and Planck time, the concept of smooth temporal flow may break down entirely. The Planck time, which is approximately 10 to the negative 43 seconds, represents the smallest meaningful interval of time, according to our current understanding of physics. If time is indeed quantized at this scale, then the smooth flow of time that we experience may be an approximation, valid only at scales much larger than the Planck scale. The quantization of time at the Planck scale would mean that temporal flow is not continuous, but consists of discrete jumps, like frames in a cosmic movie playing at an unimaginably fast frame rate. The smooth flow of time that we experience would emerge from our inability to perceive these incredibly brief temporal intervals. Much like the smooth motion we see in movies emerges from rapidly displayed still frames. This possible quantization of time is intimately connected to the speed of light through the definition of the Planck time itself. The Planck time is defined in terms of fundamental constants, including the speed of light, Planck's constant, and the gravitational constant. If time is indeed quantized at this scale, then the speed of light helps determine the finest possible resolution of temporal experience. The flow of time also depends on the thermodynamic arrow of time, the direction in which entropy increases. This thermodynamic arrow emerges from statistical mechanics and the behavior of large numbers of particles. But even this statistical behavior depends on the interactions between particles, interactions that propagate at light speed through electromagnetic and other fields. The arrow of time that we experience in everyday life, the direction from past to future, may thus be another manifestation of light-speed limited processes. Consider the simple act of remembering a past event. Memory formation involves changes in the connections between neurons, changes that propagate through your nervous system at finite speed. The asymmetry between memory and prediction, between our detailed knowledge of the past and our uncertainty about the future, may reflect the light-speed limited nature of information processing in biological systems. We remember the past because information about past events has had time to propagate to us and be processed by our brains. We cannot remember the future because information about future events has not yet had time to reach us. The flow of time also appears in the expansion of the universe itself. As space expands, it carries light along with it, stretching the wavelengths of photons and creating the cosmological redshift that we observe in distant galaxies. This expansion affects the propagation of light across cosmic distances and creates a kind of cosmic flow that may be related to our experience of temporal flow. The acceleration of cosmic expansion, driven by the mysterious dark energy, adds another layer to the relationship between light and temporal flow. As the expansion accelerates, distant regions of the universe become increasingly disconnected from us, with light from these regions becoming increasingly redshifted and delayed. This cosmic acceleration may represent a kind of temporal stretching that affects the flow of time on the largest scales. The study of temporal flow has also revealed connections to consciousness and the nature of subjective experience. Some researchers have proposed that consciousness itself emerges from the integration of information across different timescales, from the rapid firing of individual neurons to the slower rhythms of brainwaves and circadian cycles. All of these timescales are ultimately constrained by the speed at which information can propagate through biological systems. The binding problem in consciousness research asks how the brain integrates information from different senses and different brain regions into a unified conscious experience. This binding may depend on the synchronization of neural activity across different parts of the brain, synchronization that requires signals to travel at finite speeds through neural networks. The temporal unity of consciousness may thus be another manifestation of light-speed limited information processing. As we contemplate the deep connections between light speed and temporal flow, we begin to see that what we call the flow of time may not be a fundamental property of reality, but rather an emergent phenomenon that arises from the way information propagates through space-time. The feeling that time flows from past to future, that moments follow one another in sequence, that duration has meaning and direction, all of these aspects of temporal experience may be consequences of living in a universe where information cannot travel faster than light. The speed of light does not just limit how fast things can move through space, it may actually create the flow of time itself. In a universe where information could travel instantaneously, there might be no experience of temporal flow, no sense of duration, no feeling that time passes. It is the finite speed of light that creates the delays, the gaps, the sequences that we experience as the flow of time. This perspective suggests that time is not a river flowing from past to future, but rather a consequence of the way consciousness samples a universe where information propagates at light speed. The flow of time becomes not a fundamental aspect of reality, but a beautiful illusion created by the interplay between awareness and the cosmic speed limit, a subjective experience that emerges from the finite speed at which the universe reveals its secrets to those who wait patiently for light to complete its eternal journeys through the vast expanses of space. In the darkest corners of the universe, where gravity has triumphed over all other forces, exist objects so dense and massive that they tear holes in the very fabric of space-time itself. These are black holes, cosmic monsters that devour light and distort time in ways so extreme that they challenge our most basic understanding of reality. Near a black hole, the gentle flow of time that governs our everyday existence becomes twisted into something almost unrecognizable, stretched and warped, until seconds become hours, hours become years, and the familiar rhythm of temporal passage dissolves into a cosmic dance of relativity and quantum mechanics. To understand how black holes create the ultimate distortion of time, we must first appreciate the extraordinary conditions that exist near these cosmic giants. A black hole forms when matter becomes so compressed that its gravitational pull exceeds the ability of any known force to resist it. The matter collapses inward, creating a region of space-time curvature so extreme that the normal rules of physics are pushed beyond their limits. At the center lies the singularity, a point where density becomes infinite and the curvature of space-time becomes so severe that our current theories can no longer describe what happens. But it is not the singularity itself that creates the most dramatic effects on time. It is the event horizon, the boundary surrounding the black hole beyond which nothing, not even light, can escape. The event horizon is not a physical surface, but rather a kind of point of no return in space-time, a boundary defined by the geometry of gravity and the speed of light. Once anything crosses this boundary, it is forever cut off from the rest of the universe, trapped in a region where all paths through space-time lead inexorably toward the central singularity. The effects of black holes on time become apparent long before you reach the event horizon. As you approach a black hole, the intense gravitational field begins to warp space-time around you in ways that dramatically affect the passage of time. Time dilation near black holes operates on a scale that dwarfs the modest effects we observe in everyday life. While GPS satellites require small corrections for gravitational time dilation, near a black hole, these effects become so extreme that they dominate the entire experience of space and time. Imagine watching a friend slowly approach the event horizon of a black hole while you observe from a safe distance. As your friend gets closer to the black hole, something extraordinary happens to your perception of their journey. The intense gravitational field causes time to slow down dramatically for your friend relative to your own reference frame. From your perspective, your friend appears to move more and more slowly as they approach the event horizon. Their movements become sluggish, their gestures drawn out over increasingly long periods. But the effect goes beyond simple slow motion. As your friend approaches the event horizon, the light they emit becomes increasingly red-shifted due to the gravitational field. The photons climbing out of the gravitational well lose energy, causing the light to shift toward longer, redder wavelengths. Your friend appears to fade from view, becoming dimmer and redder until they seem to freeze at the event horizon, their image preserved forever in an increasingly faint and reddened state. From your friend's perspective, however, the experience is completely different. They feel no slowing of time, no stretching of moments. Their watch continues to tick at its normal rate. Their thoughts proceed at their usual pace, and they experience a normal passage of time as they cross the event horizon and continue toward the singularity. The dramatic time dilation that you observe from a distance is not experienced by the person actually falling into the black hole. This asymmetry in temporal experience reveals something profound about the relative nature of time near extreme gravitational fields. The event horizon itself represents a kind of temporal boundary where the flow of time becomes infinitely dilated from the perspective of a distant observer. Light emitted from the event horizon takes an infinite amount of time to escape to infinity, which is why nothing can escape from beyond this boundary. The event horizon is not just a spatial boundary, but a temporal one as well, a surface in space-time, where the normal relationship between space and time breaks down in the most dramatic way possible. The mathematics of black hole time dilation reveal the intimate connection between gravity, light, and temporal experience. The gravitational time dilation near a black hole depends on what physicists call the gravitational potential, which measures how deep you are in the gravitational well created by the black hole's mass. The stronger the gravitational field, the slower time runs relative to regions of weaker gravity. Near the event horizon of a stellar mass black hole, time can be dilated by factors of millions or billions compared to time measured far from the black hole. For supermassive black holes, which can contain millions or billions of times the mass of our Sun, the effects are even more dramatic. These cosmic giants, found at the centers of most galaxies, create gravitational fields so intense that they can slow time by factors that are almost incomprehensible. An astronaut who somehow survived a journey near such a black hole could experience minutes while billions of years pass in the outside universe. But black holes create more than just time dilation. They also create tidal effects that stretch space and time in different directions. The gravitational field of a black hole is not uniform, but varies with distance from the center. This variation creates tidal forces that stretch objects in the radial direction, while compressing them in the tangential directions. Near a black hole, these tidal effects extend to space-time itself, creating a differential stretching of time that depends on your position, relative to the black hole. The study of black holes has revealed that the relationship between gravity and time is even more subtle than Einstein originally imagined. Quantum effects near black holes create phenomena that challenge our understanding of both gravity and quantum mechanics. One of the most famous of these is Hawking radiation, the prediction that black holes actually emit radiation and slowly evaporate over time. Hawking radiation arises from quantum fluctuations in the vacuum near the event horizon. These fluctuations normally produce pairs of virtual particles that quickly annihilate each other. But near the event horizon, the extreme curvature of space-time can separate these particle pairs, with one particle falling into the black hole, while the other escapes to infinity. The escaping particles carry energy away from the black hole, causing it to slowly shrink and eventually evaporate completely. The timescale for black hole evaporation through Hawking radiation is staggering. A black hole with the mass of our Sun would take approximately 10 to the 67th years to evaporate completely, a time so long that it dwarfs the current age of the universe by an almost unimaginable factor. For more massive black holes, the evaporation time is even longer. Yet this process reveals something profound about the relationship between gravity, quantum mechanics, and time. The temperature of Hawking radiation is inversely related to the mass of the black hole, which means that smaller black holes are actually hotter than larger ones. As a black hole evaporates and loses mass, it becomes hotter and radiates faster, creating a runaway process that accelerates the evaporation. In the final moments of a black hole's life, it would explode in a burst of radiation, releasing all of its remaining mass energy in a fraction of a second. The information paradox associated with black hole evaporation raises deep questions about the nature of time and causality. If information that falls into a black hole is destroyed when the black hole evaporates, this would violate one of the fundamental principles of quantum mechanics, which states that information cannot be destroyed. Some proposals to resolve this paradox suggest that time itself near black holes may be more complex than we currently understand. One possibility is that the interior of a black hole is connected to the exterior through quantum entanglement in ways that transcend our classical understanding of space and time. Another possibility is that the singularity at the center of a black hole is not actually reached in finite time, and that information is preserved through subtle quantum effects that operate on timescales longer than the age of the universe. The study of black holes has also led to insights about the holographic nature of space-time. The holographic principle suggests that all the information contained within a volume of space can be encoded on the boundary of that volume. For black holes, this means that all the information that falls into the black hole may be encoded on the event horizon, preserved in a two-dimensional representation of the three-dimensional interior. If the holographic principle is correct, it suggests that our three-dimensional experience of space may be emergent from more fundamental two-dimensional processes. This would mean that the flow of time in 3 dimensions is actually a projection of more fundamental temporal processes operating on 2-dimensional boundaries. The connection between black holes and holography hints that time itself may be emergent rather than fundamental. Rotating black holes, known as Kerr black holes, create even more exotic effects on spacetime and time. The rotation of these black holes drags spacetime around with it, creating a phenomenon called frame dragging. In the ergosphere, the region outside the event horizon where frame dragging dominates, spacetime itself is dragged around the black hole at nearly the speed of light. In this region, it becomes impossible to remain stationary relative to distant observers, as all reference frames are dragged along with the rotating spacetime. The interaction between rotation and gravity in Kerr black holes creates the possibility of closed time-like curves, paths through spacetime that loop back to their own past. While these curves exist mathematically in the spacetime geometry around rotating black holes, it is unclear whether they represent physical possibilities or are artifacts of our incomplete understanding of quantum gravity effects. Black holes also serve as natural laboratories for testing the limits of our understanding of space and time. The extreme conditions near black holes push the boundaries of both general relativity and quantum mechanics, revealing the need for a unified theory of quantum gravity. Such a theory might show that the singularities at the centers of black holes are not actually singular, but are resolved by quantum effects operating at the Planck scale. The recent direct imaging of black holes by the Event Horizon Telescope has provided new insights into how these objects warp spacetime and affect the propagation of light. The shadow of a black hole, created by the bending of light around the event horizon, reveals the boundary between the region where photons can escape and the region where they are trapped forever. This shadow is a direct visualization of how extreme gravity affects the speed and direction of light. As we contemplate the extreme warping of time near black holes, we see how gravity and light conspire to create the most dramatic distortions of temporal experience in the known universe. The event horizon represents the ultimate boundary where light speed and gravitational effects combine to create a region of spacetime that is forever cut off from external observation. The time dilation near black holes reveals that time is not absolute, but is intimately connected to the curvature of space-time and the propagation of light through that curved geometry. Black holes show us time at its most extreme, stretched and warped, until the familiar flow of moments becomes something alien and strange. Yet even in these extreme environments, the speed of light remains the fundamental constant that determines how information propagates and how cause relates to effect. The distortion of time near black holes is not a violation of the role of light in shaping temporal experience, but rather its ultimate expression, showing us what happens when the relationship between light, gravity, and time is pushed to its absolute limits. In the darkness surrounding black holes, where light itself cannot escape, we find perhaps the clearest evidence that time is not the absolute universal flow we imagine it to be, but rather a flexible aspect of space-time that responds to the most extreme conditions in the universe. The warping of time near black holes brings us face to face with the possibility that our everyday experience of temporal flow is just one manifestation of a deeper, more complex relationship between consciousness, light, and the geometry of the cosmos. In the strange and wonderful realm of quantum mechanics, where particles exist in multiple places at once, and the act of observation changes reality itself, time reveals yet another layer of mystery. Here, in the domain of the infinitesimally small, the familiar flow of moments that governs our everyday experience gives way to something far more puzzling. Quantum particles seem to exist outside the normal rules of temporal sequence, engaging in behaviors that challenge our most basic assumptions about causality, simultaneity, and the very nature of temporal existence. And at the heart of these quantum mysteries lies light itself, not as the familiar waves and particles of classical physics, but as quantum fields that fluctuate in ways that may hold the key to understanding whether time is fundamental or emergent. To appreciate how quantum mechanics transforms our understanding of time, we must first confront the wave-particle duality that lies at the heart of quantum theory. Light, which we have been exploring as the cosmic speed limit that shapes temporal experience, reveals itself in the quantum realm to be both wave and particle simultaneously. Photons, the quantum particles of light, exhibit behaviors that seem to transcend the normal limitations of space and time, existing in quantum superpositions that allow them to be in multiple states and locations simultaneously. This quantum nature of light creates profound puzzles for our understanding of temporal sequence. In the famous double-slit experiment, photons appear to pass through both slits simultaneously, creating interference patterns that can only be explained if the photons exist in a superposition of states. But this superposition seems to exist outside the normal flow of time, in a kind of quantum limbo where events have not yet crystallized into definite outcomes. The act of measurement in quantum mechanics introduces another layer of temporal mystery. When we observe a quantum system, the superposition collapses and the system assumes a definite state. But this collapse appears to happen instantaneously, regardless of the size of the system or the distance over which the superposition extends. This instantaneous collapse seems to violate the speed of light limit that governs all other physical processes, suggesting that quantum mechanics operates according to temporal rules that are fundamentally different from those of classical physics. The uncertainty principle, one of the cornerstones of quantum mechanics, creates fundamental limits on how precisely we can know certain pairs of properties simultaneously. The most famous version involves position and momentum, but there is also an energy-time uncertainty relation that has profound implications for our understanding of temporal existence. This relation tells us that the more precisely we try to measure when a quantum event occurs, the less precisely we can know the energy involved in that event. This energy-time uncertainty creates a fundamental fuzziness in the temporal structure of quantum events. At the smallest scales, quantum events cannot be said to occur at definite times with definite energies. Instead, they exist in a kind of temporal probability cloud, where the concepts of when and how much energy become fundamentally intertwined. This quantum fuzziness in time may be telling us something profound about the nature of temporal existence at the most fundamental level of reality. The quantum vacuum, the lowest energy state of quantum fields, is far from empty despite its name. It seethes with virtual particles that pop into and out of existence on timescales determined by the uncertainty principle. These quantum fluctuations create a kind of temporal foam at the smallest scales, where the smooth flow of time breaks down into a chaotic dance of creation and annihilation. The duration of these quantum events is limited by the uncertainty principle, with more energetic virtual particles having shorter lifetimes. This quantum foam suggests that time itself may not be continuous at the smallest scales, but may instead consist of discrete, quantized units. The Planck time, approximately 10 to the negative 43 seconds, represents the smallest meaningful interval of time according to our current understanding of physics. Below this scale, the concepts of before and after may lose their meaning entirely, replaced by quantum superpositions of temporal states. The relationship between quantum mechanics and light becomes even more intriguing when we consider quantum field theory, the framework that unifies quantum mechanics with special relativity. In this theory, light is understood as excitations of the electromagnetic field, a quantum field that permeates all of space-time. But the quantum electromagnetic field exhibits properties that seem to transcend the classical limitations of light speed propagation. Quantum entanglement, perhaps the most mysterious aspect of quantum mechanics, creates instantaneous correlations between particles regardless of the distance separating them. When two particles become entangled, measuring the properties of one particle instantly determines the properties of the other, even if they are separated by vast distances. This instantaneous correlation seems to violate the speed of light limit, suggesting that quantum mechanics operates according to principles that transcend the classical relationship between light and time. Einstein famously called entanglement spooky action at a distance and was deeply troubled by its implications for the nature of reality. He believed that there must be hidden variables that predetermined the outcomes of quantum measurements, preserving the local nature of physical interactions and the supremacy of light speed as the ultimate speed limit. But decades of experiments have confirmed that entanglement is real, and that there are no hidden variables that can explain away its non-local character. The resolution to this apparent paradox lies in understanding that entanglement does not allow the transmission of information faster than light. While the correlations between entangled particles are instantaneous, these correlations cannot be used to send messages or transfer energy faster than light speed. The quantum correlations exist in a kind of temporal limbo that transcends classical causality while still respecting the fundamental prohibition against faster than light communication. This suggests that quantum mechanics reveals a deeper layer of reality where the normal rules of temporal sequence and causal connection are supplemented by more fundamental quantum relationships. These relationships may exist outside the normal flow of time, in a kind of quantum eternity where past, present, and future are unified in ways that classical physics cannot comprehend. The quantum Zeno effect provides another example of how quantum mechanics can alter the flow of time. This effect occurs when frequent measurements of a quantum system prevent it from evolving to other states. By observing a quantum system continuously, we can effectively freeze its evolution, trapping it in its initial state despite the passage of time. This suggests that the act of observation itself can influence the flow of time at the quantum level. The relationship between quantum mechanics and consciousness adds another layer of mystery to the quantum nature of time. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in collapsing quantum superpositions and determining the outcomes of measurements. If consciousness is indeed required to collapse quantum states, then the emergence of definite temporal sequences may depend on the presence of conscious observers. This possibility raises profound questions about the nature of time in a universe without consciousness. If quantum superpositions exist outside the normal flow of time, and if consciousness is required to collapse these superpositions into definite temporal sequences, then time as we experience it may be fundamentally dependent on the existence of conscious observers. In a universe without consciousness, reality might exist in a kind of quantum superposition, where all possible temporal sequences coexist simultaneously. Quantum computing exploits the strange temporal properties of quantum mechanics to perform calculations that would be impossible with classical computers. Quantum computers can exist in superpositions of computational states, effectively exploring multiple computational paths simultaneously. These quantum computations seem to occur outside the normal constraints of temporal sequence, allowing quantum computers to solve certain problems exponentially faster than classical computers. The development of quantum technologies has also revealed new aspects of the relationship between quantum mechanics and time. Quantum clocks, which use quantum superpositions to measure time intervals, can achieve precision that surpasses classical atomic clocks. These quantum clocks reveal that time measurement itself is fundamentally quantum mechanical, depending on quantum transitions between energy levels that exist in superposition until the moment of measurement. Quantum field theory also predicts the existence of quantum fluctuations in space-time itself at the Planck scale. These fluctuations suggest that the fabric of space-time may be fundamentally quantum mechanical, with space and time existing in superpositions at the smallest scales. If space-time itself is quantum mechanical, then the classical notion of a smooth, continuous flow of time may be an approximation that emerges only at larger scales. The study of quantum gravity, which attempts to unify quantum mechanics with general relativity, has revealed even more exotic possibilities for the quantum nature of time. Some theories suggest that time may be emergent rather than fundamental, arising from more basic quantum processes that operate outside the normal framework of temporal existence. In these theories, time is not a pre-existing stage upon which quantum events unfold, but rather a collective property that emerges from quantum interactions. The holographic principle, which suggests that the information in a volume of space can be encoded on its boundary, has quantum mechanical implications for the nature of time. If reality is fundamentally holographic, then the three-dimensional flow of time that we experience may be a projection of more fundamental two-dimensional quantum processes. This would mean that time as we know it is not fundamental, but is rather an emergent property of quantum information processing. Quantum error correction, a technique developed for quantum computing, may also provide insights into the nature of time and reality. Some researchers have suggested that space-time itself may be maintained by quantum error correction processes that preserve the classical appearance of space and time, despite underlying quantum fluctuations. In this view, the smooth flow of time is actively maintained by quantum processes that prevent the accumulation of quantum errors. The relationship between quantum mechanics and thermodynamics also provides clues about the quantum nature of time. The second law of thermodynamics, which describes the increase of entropy over time, emerges from the statistical behavior of large numbers of particles. But at the quantum level, the relationship between entropy and time becomes more complex, with quantum coherence playing a role in determining the direction of temporal evolution. As we explore the quantum nature of time, we encounter the possibility that time as we experience it may not exist at the most fundamental level of reality. Instead, temporal experience may emerge from quantum processes that operate according to principles that transcend classical notions of sequence, causality, and duration. Light, in its quantum form as electromagnetic fields and photons, may be the bridge between the quantum realm, where time is fuzzy and probabilistic, and the classical realm, where time flows smoothly from past to future. The quantum nature of light reveals that even our most basic understanding of electromagnetic radiation must be reconsidered in light of quantum mechanics. Photons exist in quantum superpositions, exhibit wave-particle duality, and participate in entanglement relationships that transcend classical space and time. These quantum properties of light may be essential to understanding how temporal experience emerges from more fundamental quantum processes. If time is indeed emergent from quantum processes, then our experience of temporal flow may be fundamentally dependent on the quantum nature of light and matter. The smooth, continuous time of everyday experience may be a collective illusion created by the averaging of countless quantum events, each of which exists in a probabilistic superposition until the moment of measurement or interaction. In this quantum view of time, the question of whether time exists without light takes on new meaning. Light, in its quantum form, may not just reveal the structure of time, but may actually participate in creating temporal experience through quantum field fluctuations, virtual particle processes, and the collapse of quantum superpositions. The quantum nature of time suggests that the relationship between light and temporal experience is even deeper and more fundamental than classical physics would suggest, extending into the very foundations of reality, where the concepts of space, time, and causality themselves emerge from quantum mechanical processes that operate according to principles we are only beginning to understand. As we stand at the threshold of understanding time's deepest mysteries, we find ourselves confronting questions that reach far beyond the realm of physics into the very heart of what it means to exist, to be conscious, to live and love and dream in a universe where time itself may be nothing more than a beautiful illusion. If our journey through relativity, quantum mechanics, and the nature of light has taught us anything, it is that time is far stranger and more malleable than our everyday experience suggests. But what does it mean for human existence if time, the most intimate aspect of our conscious experience, turns out to be a construction rather than a fundamental feature of reality? The possibility that time is an illusion created by the speed of light forces us to reconsider everything we think we know about the nature of existence. Our entire sense of self, our memories of the past, our hopes for the future, our experience of growth and change and loss, all of these fundamental aspects of human experience are built upon the assumption that time is real and that moments follow one another in a meaningful sequence. If time is indeed an illusion, then what are we to make of our temporal existence? To explore these profound implications, we must first understand what we mean when we say that time might be an illusion. We do not mean that temporal experience is imaginary or unreal in the sense that hallucinations are unreal. Our experience of duration, sequence, and temporal flow is undeniably real as a subjective phenomenon. What we mean is that this experience may not correspond to any fundamental aspect of reality itself, but may instead emerge from the way consciousness interacts with information that propagates at the speed of light through space-time. Consider the analogy of a rainbow. When you see a rainbow stretching across the sky, your visual experience is completely real and valid. The colors are vivid, the arc is clearly defined, and the beauty is undeniable. Yet we know that the rainbow does not exist as a physical object in the sky. It is an optical illusion created by the interaction between sunlight, water droplets, and your visual system. The rainbow emerges from the particular way light interacts with matter and consciousness, but it has no independent existence apart from these interactions. Time may be similar to a rainbow in this sense. Our experience of temporal flow, of moments following one another in sequence, of duration and change and becoming, may be completely real as subjective experiences while having no fundamental existence in the structure of reality itself. Time may emerge from the particular way consciousness interacts with information propagating at light speed, creating the illusion of temporal passage, even though the underlying reality is static and eternal. This perspective aligns with the block universe interpretation of relativity, which suggests that all events in space-time exist simultaneously in a four-dimensional continuum. From this view, past, present, and future are equally real, and the flow of time is nothing more than the subjective experience of consciousness moving through this static block universe. Your birth, your current moment of existence, and your eventual death all exist as permanent features of the space-time manifold, as real and enduring as mountains and valleys in a landscape. But if the block universe interpretation is correct, what creates the subjective experience of temporal flow? Why do we experience moments sequentially rather than simultaneously? The answer may lie in the way consciousness processes information that arrives at the speed of light from different events and locations. Our brains construct the experience of now by integrating sensory information, memories, and internal processes that all propagate at light speed through neural networks. This integration process takes time, not because time is fundamental, but because information processing requires sequential operations that unfold according to the causal structure determined by light speed. The feeling that time flows may emerge from the way consciousness samples the block universe, creating a moving spotlight of awareness that illuminates different regions of space-time in sequence. The spotlight itself may be an illusion, but the regions it illuminates are as real and permanent as anything in the universe. Different philosophical traditions have grappled with the nature of time for millennia, often arriving at insights that seem to anticipate modern physics. In Buddhism, the concept of impermanence teaches that all phenomena are in constant flux, but this flux itself is understood to be an illusion that obscures the underlying emptiness and interconnectedness of all things. The Buddhist notion of the eternal now, where past and future collapse into a timeless present, resonates with the block universe interpretation of relativity. Hindu philosophy speaks of the cyclical nature of time, with vast cosmic cycles of creation and destruction playing out over billions of years. But beyond these cycles lies Brahman, the eternal and unchanging reality that transcends all temporal distinctions. In this view, time is Maya, a cosmic illusion that veils the timeless truth of existence. The speed of light as the fundamental constant that shapes temporal experience might be understood as one of the mechanisms through which this cosmic illusion is maintained. Ancient Greek philosophers also wrestled with the nature of time and change. Heraclitus taught that everything flows and that you cannot step into the same river twice, emphasizing the reality of temporal change. But Parmenides argued that change is an illusion and that true reality is eternal and unchanging. Plato tried to reconcile these views by distinguishing between the world of appearances, where time and change seem real, and the world of eternal forms, where true reality exists outside of time. The implications of time as an illusion extend deeply into questions of personal identity and the continuity of the self. If time is not fundamental, then what creates the sense of being a continuous self that persists through time? Your memory of being a child, your current adult identity, and your future elderly self may all exist simultaneously in the block universe, connected not by temporal flow, but by causal and informational relationships that propagate at light speed. This raises profound questions about responsibility, growth, and change. If all moments of your life exist simultaneously, in what sense do you learn and grow and become wiser over time? The answer may lie in understanding that while all moments exist equally, they exist in specific causal relationships determined by the light-speed propagation of information. The child you were influences the adult you are through causal chains that respect the cosmic speed limit, creating the appearance of temporal development even in a timeless reality. The illusion of time also has implications for our understanding of death and mortality. In our everyday experience, death represents the end of temporal existence, the cessation of the flow of conscious moments. But if time is an illusion and all moments exist equally, then death may not be the absolute ending it appears to be. Your entire life, from birth to death, may exist as a permanent feature of the space-time manifold, as real and enduring as a mountain range. This does not mean that death is not real or significant as an experience. The moment of death, and all the moments leading up to it, are as real as any other moments in your life. But these moments may not represent the end of existence so much as the boundary of a particular pattern of consciousness within the eternal block universe. Your life may be like a river flowing through a landscape, with death marking not the destruction of the water, but simply the point where this particular stream merges back into the ocean of existence. The implications extend to our understanding of free will and determinism. If all moments exist simultaneously in a block universe, then the future already exists in the same sense that the past exists. This seems to suggest that everything is predetermined and that free will is an illusion. But the relationship between the block universe and free will is more subtle than it initially appears. The key insight is that the block universe does not imply that events are predetermined by some external force or cosmic plan. Instead, it suggests that the distinction between determination and freedom may itself be based on the illusion of temporal flow. In a timeless reality, the question is not whether the future is predetermined, but whether the patterns of causality and choice that connect different regions of space-time are consistent with our understanding of agency and responsibility. Your choices may be real and meaningful, not because they determine a previously open future, but because they are genuine features of the causal structure of space-time. The decision you make right now to continue reading these words is as real and as much your own choice as it would be in a universe with flowing time. The reality of choice does not depend on the future being open, but on the choice being genuinely yours, genuinely connected to your values and reasoning processes. The illusion of time also transforms our understanding of love, relationships, and human connection. If all moments exist simultaneously, then every moment of love you have ever experienced or will experience exists eternally in the block universe. The love between partners, the bond between parent and child, the friendship that sustains you through difficult times, all of these connections exist as permanent features of reality, not subject to the erosion of temporal passage. This does not diminish the poignancy of loss or the joy of reunion, but it places these experiences in a broader context. When you lose someone you love, you are not losing their existence, but rather experiencing the boundary between the region of space-time where you share experiences and the region where your paths diverge. The love itself, the moments of connection and understanding and shared joy, remain as permanent features of the cosmic landscape. The creative arts have long intuited the illusory nature of time, creating works that seem to exist outside the normal flow of temporal experience. Music unfolds in time, yet a great musical composition seems to exist as a complete, eternal structure that we experience sequentially only because of the limitations of consciousness. Poetry captures moments and makes them eternal, freezing temporal experience into patterns of language that transcend the flow of time. Visual arts create spatial representations of temporal experience, allowing us to see movement, change, and duration in static images. Cinema creates the illusion of temporal flow from a sequence of still images, much like consciousness might create the illusion of time from a sequence of static moments in the block universe. These artistic insights suggests that humans have always sensed the constructed nature of temporal experience. The illusion of time also has implications for our understanding of suffering and healing. Much human suffering is rooted in attachment to temporal concepts, regret over the past, anxiety about the future, the feeling that happiness is fleeting and loss is permanent. If time is an illusion, then these forms of suffering are based on a fundamental misunderstanding of the nature of reality. This does not mean that pain and loss are not real as experiences, but it suggests that the temporal framework within which we usually understand these experiences may be adding unnecessary layers of suffering. The pain of loss may be real, but the belief that what is lost is gone forever may be based on the illusion of temporal flow. The anxiety about an uncertain future may be real, but the belief that the future is fundamentally different from the present may be based on a misunderstanding of time's nature. Healing, in this context, might involve learning to see through the illusion of time to the eternal reality that lies beneath temporal experience. This does not mean abandoning all temporal concerns or acting as if time does not matter, but rather developing a deeper perspective that recognizes both the reality of temporal experience and its ultimate illusory nature. The practical implications of understanding time as an illusion are still being explored by philosophers, psychologists, and spiritual teachers. Some suggest that recognizing the illusory nature of time can lead to greater peace, reduced anxiety, and a deeper appreciation of present moment experience. Others worry that such recognition might lead to fatalism or a diminished sense of responsibility for our actions. The truth may lie in a middle path that honors both the reality of temporal experience and its ultimate illusory nature. We can live fully within time while understanding that time itself may be a construction. We can take responsibility for our choices while recognizing that those choices exist eternally in the block universe. We can love deeply and grieve genuinely while understanding that love and loss are permanent features of reality rather than temporary experiences subject to the erosion of time. As we contemplate the possibility that time is an illusion created by the speed of light, we are invited to reconsider not just our understanding of physics and cosmology, but our understanding of what it means to be human. The illusion of time may be one of the most beautiful and profound constructions in the universe, creating the subjective experience of existence, growth, love, and meaning within a reality that is ultimately timeless and eternal. Understanding this illusion does not diminish its beauty or importance, but rather deepens our appreciation for the extraordinary complexity and richness of conscious experience in a cosmos shaped by the eternal dance of light through space-time. As we stand on the threshold of unprecedented scientific discovery, gazing out into a universe that continues to reveal its deepest secrets, we find ourselves at a remarkable moment in human understanding. The mysteries of time, space, and light that have puzzled philosophers and scientists for millennia are beginning to yield to new theoretical frameworks, experimental techniques, and computational tools that promise to transform our comprehension of reality itself. The future of physics holds the potential to either confirm our emerging understanding of time as an illusion created by light speed, or to reveal even more profound truths about the nature of temporal existence. The quest to understand time's true nature is driving some of the most ambitious research programs in modern physics. Quantum gravity, the long-sought theory that would unify quantum mechanics with general relativity, promises to reveal how space and time emerge from more fundamental quantum processes. Several competing approaches to quantum gravity are being pursued, each offering different insights into the possible nature of time at the most fundamental level of reality. String theory, one of the leading candidates for a theory of quantum gravity, suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in multiple spatial dimensions. In string theory, time emerges from the vibrational patterns of these strings. and the speed of light appears as a consequence of the geometry of the higher dimensional space in which the strings vibrate. If string theory is correct, then time and light speed are both emergent properties of more fundamental, stringy dynamics. Loop quantum gravity takes a different approach, suggesting that space and time themselves are quantized at the Planck scale. In this theory, space-time is composed of discrete units, like atoms of space and time, that combine to create the smooth space-time we observe at larger scales. The quantization of time in loop quantum gravity suggests that temporal flow may indeed be an approximation that emerges from the averaging of discrete temporal events occurring at the Planck scale. Causal set theory proposes that space-time is fundamentally composed of discrete events connected by causal relationships. In this framework, time emerges from the causal ordering of events, and the speed of light represents the fundamental rate at which causal influences can propagate through the discrete space-time structure. This approach suggests that both time and light speed are emergent properties of the underlying causal geometry of reality. The holographic principle, inspired by the physics of black holes, suggests that all the information in a volume of space can be encoded on its boundary. If reality is fundamentally holographic, then the three-dimensional world we experience, including the flow of time, may be a projection of information processing on two-dimensional surfaces. This would mean that time as we know it is not fundamental, but is rather a way of organizing information in higher dimensional projections. Advances in quantum computing are opening new avenues for exploring the relationship between information, time, and consciousness. Quantum computers can perform certain calculations exponentially faster than classical computers by exploiting quantum superposition and entanglement. These quantum advantages suggest that information processing in quantum systems may operate according to temporal principles that differ fundamentally from classical information processing. The development of quantum simulators, specialized quantum computers designed to simulate quantum many-body systems, is providing new insights into how temporal behavior emerges from quantum dynamics. These simulators can explore regimes of quantum behavior that are impossible to study with classical computers, potentially revealing new aspects of how time emerges from quantum processes. Artificial intelligence and machine learning are also contributing to our understanding of time and consciousness. Neural networks that can process temporal sequences are providing insights into how brains might construct the experience of temporal flow from sequential information processing. These AI systems suggest that the subjective experience of time might emerge from the particular way information is processed and integrated in complex networks. The study of consciousness itself is being revolutionized by new experimental techniques and theoretical frameworks. Integrated information theory suggests that consciousness corresponds to the amount of information integrated by a system, and that the temporal aspects of consciousness emerge from the dynamics of information integration. If consciousness is indeed a measure of information integration, then the relationship between consciousness and time may be even deeper than previously suspected. Advances in neuroscience are revealing how the brain constructs temporal experience from neural activity. The discovery of neural oscillations that synchronize brain activity across different regions suggests that the temporal unity of consciousness may emerge from the coordination of these oscillatory patterns. The frequencies of these oscillations are limited by the speed at which signals can propagate through neural networks, creating another connection between information processing speed and temporal experience. The development of brain-computer interfaces and direct neural stimulation techniques is providing unprecedented insights into how temporal experience can be altered or manipulated. Patients with deep brain stimulation devices sometimes report alterations in their sense of time, suggesting that temporal experience is intimately connected to specific patterns of neural activity that can be modified technologically. Cosmological observations are also contributing to our understanding of time's nature. The discovery of gravitational waves has opened a new window into the universe, allowing us to observe how extreme gravitational events affect the fabric of space-time itself. Future gravitational wave detectors may be sensitive enough to detect quantum fluctuations in space-time, providing direct experimental access to the quantum nature of space and time. The study of dark energy and the accelerating expansion of the universe is revealing new aspects of how space-time behaves on the larger scales. Dark energy may represent a fundamental property of space-time itself, and understanding its nature could provide insights into whether time and space are emergent or fundamental. If dark energy is indeed a property of space-time, then the acceleration of cosmic expansion may be telling us something profound about the nature of temporal existence. The search for extra dimensions, motivated by string theory and other approaches to quantum gravity, could revolutionize our understanding of space and time. If our four-dimensional space-time is embedded in a higher dimensional space, then what we experience as time may be just one aspect of a more complex multi-dimensional reality. The speed of light in our three-dimensional space might emerge from the geometry of these higher dimensions. Experimental tests of the foundations of quantum mechanics continue to reveal new aspects of how quantum systems behave in space and time. Recent experiments with quantum superposition and entanglement are pushing the boundaries of our understanding of how quantum systems exist in temporal superposition. These experiments may eventually reveal whether time itself can exist in quantum superposition. The development of atomic clocks with unprecedented precision is enabling new tests of relativity and quantum mechanics. These ultra-precise clocks can detect gravitational time dilation effects over distances of centimeters, opening new possibilities for studying how gravity affects time at laboratory scales. Future atomic clocks may be precise enough to detect quantum gravitational effects, providing experimental access to the quantum nature of time. Space-based experiments are providing new opportunities to test the fundamental nature of space and time. Missions like the Laser Interferometer Space Antenna will detect gravitational waves from space, providing access to gravitational phenomena that cannot be observed from Earth. These space-based observations may reveal new aspects of how massive objects affect the fabric of space-time. The possibility of time travel, long relegated to science fiction, is being seriously studied by theoretical physicists. While closed time-like curves remain highly speculative, the mathematical possibility of time travel in certain space-time geometries raises profound questions about the nature of causality and temporal existence. If time travel is possible, even in principle, it would fundamentally change our understanding of time's nature. The study of information theory and its relationship to physics is revealing deep connections between information, entropy, and time. The idea that information cannot be destroyed, known as information conservation, has implications for how we understand the relationship between quantum mechanics and gravity. If information is indeed conserved, then the apparent loss of information in black holes or the heat death of the universe may not represent true destruction, but rather transformation into forms we do not yet understand. The development of quantum error correction and fault-tolerant quantum computing is providing insights into how complex systems can maintain coherence despite environmental interference. Some researchers have suggested that space-time itself may be maintained by quantum error correction processes, preserving the classical appearance of space and time despite underlying quantum fluctuations. The study of emergent phenomena in complex systems is revealing how higher-level properties can arise from simpler underlying dynamics. Time itself may be an emergent property that arises from more fundamental processes, much like temperature emerges from the motion of atoms or consciousness emerges from neural activity. Understanding emergence may be key to understanding how temporal experience arises from timeless underlying reality. Advances in mathematics, particularly in the areas of category theory and topos theory, are providing new frameworks for understanding the foundations of physics. These mathematical tools may reveal new ways of thinking about space, time, and causality that transcend our current conceptual limitations. The mathematics of the future may provide the language needed to describe a reality where time and space are emergent rather than fundamental. The integration of ancient wisdom traditions with modern physics is creating new perspectives on the nature of time and consciousness. Contemplative practices from various traditions that involve altered states of consciousness are being studied scientifically, revealing how subjective temporal experience can be modified through mental training. These studies suggest that the relationship between consciousness and time may be more plastic than previously believed. The development of virtual and augmented reality technologies is creating new possibilities for studying temporal perception. These technologies can create controlled environments where temporal relationships can be manipulated, providing insights into how the brain constructs temporal experience. Virtual reality experiments may reveal the extent to which temporal experience is constructed rather than directly perceived. As we look toward the future of time research, we see a convergence of multiple fields of inquiry, all pointing toward a deeper understanding of temporal existence. Physics, neuroscience, computer science, mathematics, and philosophy are all contributing pieces to a puzzle that may eventually reveal the true nature of time and its relationship to light, consciousness, and reality itself. The implications of these future discoveries could be profound, potentially transforming not just our scientific understanding, but our entire worldview. If time is indeed revealed to be an illusion created by the speed of light, this could fundamentally change how we understand existence, consciousness, and our place in the universe. Such a discovery would rank among the greatest conceptual revolutions in human history, comparable to the realization that the Earth orbits the Sun or that species evolve through natural selection. But even if future research reveals that time is more fundamental than current theories suggest, the journey of exploration itself will have been invaluable. The questions we are asking about time, consciousness, and reality are pushing the boundaries of human knowledge and capability in ways that will benefit our understanding regardless of the specific answers we discover. The future of time research promises to be an exciting adventure of discovery, one that will require the best of human creativity, ingenuity, and collaboration. As we continue to probe the deepest mysteries of existence, we remain humbled by the vastness of what we do not yet know, while inspired by the remarkable progress we have already made in understanding the nature of time, light, and the cosmos that contains us all. The quest to understand whether time is an illusion created by the speed of light represents more than just scientific curiosity. It represents humanity's deepest desire to understand our place in the universe and the nature of our existence within it. As we continue this quest, we carry with us the hope that the universe will continue to reveal its secrets to those who approach it with wonder, patience, and an unwavering commitment to understanding the truth, whatever that truth may turn out to be. As our cosmic journey draws to a close, we find ourselves changed by the voyage we have taken together through the deepest mysteries of time, light, and existence. We began with a simple question that seemed almost too bold to ask. Could time itself be an illusion, created by the speed of light? Through our exploration of relativity, quantum mechanics, black holes, and the fundamental nature of reality, we have discovered that this question opens doors to understanding that reach far beyond what we initially imagined. We have seen how the speed of light serves not merely as a cosmic speed limit, but as the fundamental constant that weaves space and time together into the unified fabric of space-time. We have explored how this cosmic weaving creates the delays, the sequences, the causal connections that form the foundation of our temporal experience. Light does not simply travel through time, it may actually create the very framework within which temporal existence unfolds. In the strange realm of relativity, we discovered that time is far more flexible than our everyday intuitions suggest. Time dilation shows us that the passage of time depends on motion and gravity, stretching and compressing according to the curvature of space-time. The relativity of simultaneity reveals that there is no universal now, no cosmic moment that defines the present for all observers. Instead, each conscious being carries their own definition of now, their own slice through the four-dimensional tapestry of existence. We journeyed to the event horizons of black holes, those cosmic laboratories where gravity becomes so intense that it tears apart our normal understanding of space and time. Near these cosmic giants, time itself becomes warped beyond recognition, slowing to a crawl for distant observers while maintaining its normal pace for those who fall beyond the point of no return. In these extreme environments, we glimpsed how profound the connection between gravity, light, and temporal experience truly is. In the quantum realm, we encountered mysteries that challenge our most basic assumptions about reality. Quantum superposition suggests that particles can exist in multiple states simultaneously, existing in a kind of temporal limbo, until the moment of measurement crystallizes them into definite outcomes. Quantum entanglement reveals instantaneous correlations that seem to transcend the speed of light limitations, hinting at deeper layers of reality where conventional notions of space and time may not apply. We contemplated the philosophical implications of time as an illusion, exploring what this might mean for consciousness, personal identity, love, loss, and the very meaning of existence. If time is indeed a construction rather than a fundamental aspect of reality, then our entire framework for understanding life and death, growth and change, memory and anticipation may need to be reconsidered in light of this deeper truth. Looking toward the future, we saw how cutting-edge research in quantum gravity, neuroscience, and cosmology promises to reveal even more about the nature of temporal existence. The next decades may bring discoveries that either confirm our emerging understanding of time as an emergent property of light-speed interactions, or reveal even more profound truths about the relationship between consciousness, information, and the structure of reality. But perhaps the most important insight from our journey is not any specific answer about the nature of time, but rather the recognition that the questions themselves are transformative. By questioning our most basic assumptions about temporal existence, we open ourselves to new ways of understanding reality that were previously unimaginable. The willingness to consider that time might be an illusion represents a kind of intellectual courage that has driven human discovery throughout history. Whether time ultimately proves to be fundamental or emergent, real or illusory, the exploration itself expands our appreciation for the extraordinary nature of existence. We live in a universe where light races across cosmic distances at its eternal speed, where consciousness somehow emerges from the complex dance of matter and energy, where the simple act of existing involves participating in processes that stretch from the quantum scale to the cosmic horizon. The beauty of time, whether real or illusory, lies not in its absolute nature, but in its ability to create the framework within which life, consciousness, and meaning can emerge. The moments of love we share, the growth we experience, the connections we form with others, the sense of wonder we feel when contemplating the cosmos. All of these experiences have their reality and their value regardless of whether time itself is fundamental or constructed. If time is indeed an illusion created by the speed of light, then it is perhaps the most beautiful and meaningful illusion in the universe. It creates the stage upon which the drama of consciousness unfolds, the medium through which we experience growth and change and discovery. Like a master artist who uses light and shadow to create the illusion of depth and movement on a flat canvas, the universe may use the speed of light to create the illusion of temporal flow in the static space-time manifold. The rainbow analogy we explored earlier takes on deeper meaning as we conclude our journey. Just as a rainbow is both real as an experience and illusory as a physical object, time may be both real as a subjective phenomenon and illusory as a fundamental property of reality. The rainbow's beauty is not diminished by understanding its optical nature, and time's meaning is not reduced by recognizing its possible emergence from light-speed interactions. As we rest beneath the vast canopy of stars, we can feel ourselves participants in a cosmic story that unfolds on scales from the infinitesimally small to the incomprehensibly large. Each photon that enters our eyes has traveled vast distances at the speed of light, carrying information about distant events and weaving together our perception of the present moment. We are embedded in a universe where every conscious experience depends on the propagation of electromagnetic signals through neural networks at speeds ultimately limited by the cosmic speed limit. The feeling of now that accompanies your awareness of these words, the sense of duration as you contemplate these ideas, the memory of where this journey began and the anticipation of where it might lead, all of these temporal experiences may emerge from the particular way consciousness processes information that propagates at light speed through the fabric of space-time. You are not just observing the universe, you are participating in the cosmic process through which reality reveals itself to itself. In this view, consciousness becomes not separate from the physical universe, but rather the universe's way of experiencing its own existence. The speed of light is not just a constraint on physical processes, but the fundamental rhythm through which cosmic self-awareness unfolds. Time becomes not the stage upon which consciousness appears, but the mode through which consciousness experiences its own cosmic nature. The mystery of time may never be fully resolved, and perhaps that is as it should be. Mystery has always been the engine of discovery, the driving force that compels us to reach beyond our current understanding toward ever deeper truths. The fact that we can ask these questions, that we can contemplate our own temporal existence, and wonder about its ultimate nature, may be one of the most remarkable features of the universe we inhabit. As you settle into rest, let your awareness expand to encompass the vast scales of space and time that surround us. Feel yourself floating in a cosmos where light has been traveling for billions of years to create the night sky above. Sense your connection to the quantum processes that create your every thought, the relativistic effects that subtly influence your every moment, the cosmic expansion that carries you through space-time at incredible speeds. Whether time flows like a river or emerges like a rainbow, whether consciousness creates temporal experience or temporal experience creates consciousness, you are here now, aware and awake, in a universe that is far stranger and more wonderful than we have yet imagined. The speed of light connects you to the most distant galaxies and the smallest quantum fluctuations, weaving your existence into the cosmic tapestry in ways both subtle and profound. Rest now in the knowledge that the mysteries we have explored together will continue to unfold long after this moment passes. Future generations will carry forward the quest to understand time's true nature, armed with new technologies, new theories, and new insights that we can barely imagine. The questions that have guided our journey tonight will evolve and deepen, leading to discoveries that may transform our understanding of reality itself. The universe is patient with our questioning, generous with its revelations, and infinite in its capacity to surprise and inspire us. As consciousness settles into the gentle rhythms of rest and dream, we remain connected to the cosmic processes that have brought us to this moment of wonder and understanding. Time, whether fundamental or emergent, real or illusory, continues to weave its magic around us, creating the precious opportunity for awareness, for questioning, for discovery, and for the kind of deep peace that comes from contemplating our place in the infinite mystery of existence.